Talk about rigor and reproducibility and transparency. And I just want to start with a little bit of a story. So when I started college, I was actually planning to become a chemist before I got lured away into trying to understand how the mind and brain work. I'm in the psychology department here at UAB now. And in addition to loving chemistry, well, I wanted to be a chemist, and I was intrigued by its sort of mystical cousin, alchemy. And so I was, sort of professionally interested in chemistry and non-professionally interested in alchemy. And one of the things that's interesting is that we usually think about science, what makes something science as opposed to pseudoscience or non-science, is experiments and systematic data collection. But alchemists did lots of experiments and were very systematic about their data collection. The thing that made them not scientists is that they were not transparent, that their work was not reproducible. So if you were an alchemist and you found a way to turn lead into gold, you didn't share that with anybody. Or at least not the details of your method. You might tell people, I figured out a way to turn lead into gold, and show them your gold, but you would not share the actual methods of doing it with anyone other than your apprentices. So the real difference between science, or between chemistry and alchemy, and science more generally, is transparency. It's that reproducibility and transparency that we're talking about today. So the heart of science is not just the results that we care about, it's also the methods. The methods need to be replicable or reproducible, and they need to be shared in a transparent way. So that's our goal, but we've often fallen short of it. So what I'm talking about today is some factors that undermine reproducibility of science and how we can overcome them. And I want to be clear about the fact that I'm not talking about sort of outright misconduct or data fraud, right? We're not talking about making up data or other kinds of explicit fraud. What we're talking about is what's sometimes called questionable research practices. Things that old-timers like me were actually taught to do, but we now understand as being real problems for scientific methods. And so things like, you might have heard some of these terms, I'll talk about them more, p-hacking or harking. So I'll talk about that kind of stuff. So these are things that are not going to get you kicked out of the field, but will undermine the reproducibility of your work. So, all right. Just a quick overview so you have a sense of what we're doing. I'll talk about problems first. And then I'll talk about some solutions. And then I'll finish with talking about some specific NIH guidelines that you may have heard that NIH is now requiring people who submit grants to address issues of rigor and reproducibility. So I'll talk about that. I'll talk about it from the perspective of, presumably you're mostly writing them, but and I am too, but also I'm on review panels, so the guidance I get as a reviewer about how to evaluate rigor and reproducibility. Okay, so problems. Also, if there's any questions, feel free to jump in. Like I have a thing I'm going to do, but happy to stop and talk anytime, in addition to the info. Okay, problems. Landmark paper. Published in 2005, Johnny and Idis. This has been cited more than 6,000 times already, with a provocative title, Why Most Published Research Findings Are False. This is the kind of key table from it. Essentially, the probability of a finding being correct, depending on what kind of study it was. You'll see most of those values are remarkably small. And this is the short summary of why most research findings are false. Low power, small sample sizes, and high variability in the measurement mean that even if an effect is detected in a particular sample, it doesn't actually generalize outside of that sample. So the particular result that's being reported is true about the sample, but it is false about the inference, right? So again, I'm not talking about people making up data. I'm talking about the inference being wrong. And the other is bias, which is selective or distorted reporting. So if you run 20 experiments and you only report one of them,
Sorry, I'm sharing the wrong screen. Keep talking.
Okay.
I'll do this while you're talking.
All right. Step out of your way. Thank you.
Sure.
If you do 20 experiments and you only report one of them, that one that you report is true, but thank you. But you have selectively or in a distorted way reported your results, which means that in the bigger picture, the inference is false. So we'll come back to this in a little bit. But stepping back, okay, that's not. Here we go. So this is how the research cycle is supposed to work, right? You, I'm just going to find this super cool, so I'm just going to do this. You start with a hypothesis, and you design a study to test that hypothesis. You collect the data, you analyze the data, you interpret your results, you report the results, and these lead to new hypotheses, right? That's how things are supposed to work. There are problems that arise at every step in this cycle. So starting with the design part, this was a little cartoon of a fun quote that Andrew Gellman had a few years ago, where he said that some of these studies are like trying to weigh a feather using a bathroom scale, and the feather's in the pocket of a kangaroo, and the kangaroo is jumping up and down. So the claim here is not that there is no feather, or that the feather doesn't have any weight. Sure, maybe it does exist. Maybe eggs do cure cancer. But the problem is that this particular study design and data collection method are woefully inadequate to measuring that actual effect, right? And this goes back to the power issue that Ioannidis raised, that if the study design is weak, if you're dealing with a very variable effect, very small effect, and with very high variability, it's going to be very hard to detect it. And if you happen to measure it when the kangaroo lands, it's going to look like you have a very, very heavy feather. And if you happen to measure it when the kangaroo's up in the air, it looks like your feather's got negative weight, right? But in fact, it's just noise. Over here in the data analysis is what's called p-hacking. How many people have heard this term before? Or have not heard this term before? A few people have not heard. All right. So here's p-hacking. Here's how p-hacking works. Everybody knows p less than 0.05 is statistically significant, right? So what happens when you go to analyze your data, you're supposed to have an analysis plan and you run that analysis plan, right? But the reality is that you have lots of different analyses you can do, right? Slightly different regression models, include a covariate, don't include a covariate, exclude an outlier, include an outlier, that kind of stuff. You futz around with your data until you get a p-value less than 0.05, and then you report that result. Okay? That's what p-hacking is. Selective reporting of analyses that produce 0.05. You ran 100 different analyses, you got one particular combination of analysis parameters that gives you p less than 0.05, and that's what goes in the paper, and the other 99 don't. How do we know this is happening? Well, we can look at the distribution of reported p-values. And what we can see, so here's from 3 different fields, economics, psychology, and biology. And what you can see is this remarkable peak in the distribution of p-values at just under 0.05. Okay? So if people are just reporting what they find, you should get a smooth distribution of p-values. This peak just under 0.05 means that there's selective reporting happening. Right? Another way of seeing that is you could say, well, what's the proportion of p-values between 0.045 and 0.05, right? Just under that 0.05 value versus between 0.04 and 0.045, right? Just a little bit lower than that. Right? It should be about 50-50 if things are just distributed the way they should be. In fact, you see a strong bias towards p-values that are just under 0.05. And this is in different fields. So this computer and information sciences up there. Medicine and health sciences, sort of general science, multidisciplinary, and psychology. And you can see that in general you get a pretty strong bias towards these effects, right? So that's just another way of quantifying this peak. Right? So what's happening is something's going on that's leading people to report results just under 0.05 at a much higher rate than would be expected normally. Okay, that's p-hacking. Some people prefer, by the way, just quickly, some people prefer a different term. P-hacking sounds like you did something bad, which is true. It is bad. Another way of referring to it is researcher degrees of freedom, right? Because we know about, right? So we know about the degrees of freedom in our data, but there's also researcher degrees of freedom, right? Like what constitutes an outlier, what covariates we include in our model, what kind of model we use, all that kind of stuff. Those are researcher degrees of freedom, and they're typically not reported. Right? Typically, there's a bunch of choices that you made about how to do your analysis, and the ones that you stuck with are the ones that gave you a p-value less than 0.5. That's p-hacking. There's another sort of related phenomenon known as Harking that stands for hypothesizing after the results are known. Okay? So the way you're supposed to do things, right, is that you generate your hypothesis, and then you design a study, collect the data, analyze the data, and interpret the results. If the results are not what you hypothesized, a typical thing to do when you go to write your paper is to pretend that you hypothesized the results that you got. And to give you a sense of how big these, or how recent these changes are, when I was in graduate school, which was in the early 2000s, I was literally taught to do this. Right? So the first study I ran in graduate school, we got weird results. And when we got those weird results, we went to write them up. I wrote the paper, the first draft of the manuscript said, here's what we were studying, and we ran this experiment, and then we got these weird results, and here's why the results are weird. And my advisor said, no. You take that, here's why the results are weird, and you put that in the introduction of, here's what our hypothesis is. And I think, and that was pretty typical back then, as like, this is how you write a good, tight paper. Is you have your hypothesis, you have your study, right? Regardless of whether that's actually what you did or not, right? This isn't your diary. This was literally a conversation with my mentor. This isn't your diary. This isn't just step-by-step what you did. It's not a historical record. It's a report about the research results. And you put your hypothesis in the beginning, and then you put your supporting data in the results, right? That is Harking. And that vastly inflates the false positive rate. If you do a study where you collect lots of variables and you detect some unexpected interaction and then later claim that you hypothesized this interaction, you have inflated your false positives very badly. So that's Harking. Last thing I want to mention is publication bias, which is that significant outcomes, statistically significant in this case, are much more likely to be reported. And this happens both at the researcher level and at the journal level. So as a researcher, if I run an experiment and I get a non-significant result, I'm unlikely to write a paper about it and submit it to a journal. The reason I'm unlikely to do that is that many journals are not interested in publishing non-significant results. All right, so again, if I run 20 experiments, one of them comes out with a significant result, that's the one that's getting submitted. That's the typical way we do things. And that introduces a very severe publication bias. How do we know that there's publication bias? Because everything we eat both causes and prevents cancer. So these are, it's a little bit hard to read here, so these are studies of different foods and their association with cancer. So here on the negative side is protects against cancer, and this is on the positive side is causes cancer. And you can see this distinctly bimodal distribution of p-values. So what's happening, right? So you can imagine how this works, right? You run a study, large-scale study, where you collect dietary habits of lots of people, and then you test all the different foods that they ate, and you find an association for one of the 100 foods, right? Either in a positive direction or a negative direction. And then that's what ends up here, right? So if you go back here, right? So p-hacking, lots of different models, testing lots of different associations between, dietary habits and cancer. Harking, hypothesizing after the results are known that this particular dietary habit causes or prevents cancer. And then publication bias, where that's the thing that gets published. Right? So that's how you end up with this bimodal distribution. Notice that in meta-analysis, you still have this distribution, but it's pushed to the middle. Right? Because what happens is, some people find a positive association, some people find a negative association, those things get published. You do the meta-analysis, you get the drift into the middle, ideally. Meantime, presumably there's 100 other studies that show no effect that never got published. here's another example. This is, with a lot of this work, whether we choose to try to replicate a study or not depends on how sort of important that study is and provocative it is. The reproducibility project, which started in around 2011-2012, was an effort to assess the reproducibility of psychological science, my field, in a somewhat random sample, right? Not to be picking on somebody who studies relationship between dietary habits and cancer or some other particular subfield, but to try to do it in a balanced way. And the way they approached it was they picked a sample of 100 studies that were published in major psychology journals in 2008. I found out about this because one of the studies they picked was one of my studies that was published in 2008. So they contacted me in about 2011 and asked for all of my materials so that they could replicate my study. And they asked me for, what is the, you published this paper in 2008, what's the key finding there? What's the most important thing about that paper? So that we can identify that as the target of our replication. Because, most papers have multiple different kinds of things that they're reporting. And they were very careful about asking me, what are the exact materials you used? What are the exact analysis strategy that you used? What is the particular effect that's most important? And what are the parameters of the study design that really matter? So they tried very hard. So here's what they found. In the original studies, 97% of the p-values were less than 0.05. In the replications, only about 36% were less than 0.05. So this is the original studies. This is original studies and replications. Effect size, I think that is interesting, and that was sort of the high-profile finding. But what actually is very noticeable is that if you look at the effect sizes, in the original studies, all of the effect sizes were above 0, right? Again, publication bias and Harking and all that. In the replications, the effect sizes were about half of that size. So whether the p-value ends up less than 0.05 or not in the replication depends on a lot of factors. And regardless of whether it was less than 0.05 or not, the effect size was about half of it. So you can actually see that here. Here's a scatter plot of original effect sizes versus the replication. That arrow, by the way, is my study. Right there. The fact that it's a blue circle means that they did replicate a p-value less than 0.05, so in that sense my study replicated. But notice that even in that case, the effect size was about half of what I had originally reported. So, it was an adequately powered replication, so it was still significant, but the effect was substantially small. Okay. So these are the kinds of problems that we're facing in the field. Any questions about this part?
Did they replicate everything with the same N?
So they had different power. Replication power is over here, actually. So the bigger circles indicate higher replication power. There's going to be some biases in here. So my study was a study of college students doing a task on a computer. I study language processing, so it was like a word recognition task. On a computer, it was relatively easy to run a large sample. So my study had quite high replication power. My original study, I think we had 22 participants. In their replication, they had like 50. And it's easy to get 50 college students to come in and do a task on a computer. I think some of these other studies that had more complicated sampling situations did not have as high power. But independent of so in general, the studies they tried to power the studies to have 80 to 90% power, but they didn't always achieve that. Other questions? All right, so if I've convinced you to be super pessimistic about all the problems that we're facing, let's talk about how we can overcome these challenges. Turns out not to be that hard. Before I get to the actual solutions, I just want to be clear about some terminology. This, by the way, is just a graph of how we've become a lot more sensitive to issues of reproducibility. These are papers mentioning reproducibility have dramatically increased in recent decades. So reproducibility or replicability can arise at multiple levels in the study. First of all, the methods. Just in the study itself, the methods need to be described in enough detail that someone can replicate or reproduce them. the analysis methods, right? As our analysis techniques become more sophisticated, they need to be described in enough detail. Right? And the very basic form of reproducibility is that if I have your data and I have your analysis method, I will produce exactly the same results, numerically identical results. Same data, same analysis, same results. That's like the very basic, most minimal form of reproducibility. Even that's not trivial, right? We talked about if you're using a complicated analysis model and you overlook some pre-processing step or some outlier exclusion or something, you're not going to get exactly the same result, right? So that's the most basic form of reproducibility. At the results level, if I run a new study using your methods for data collection and your analysis strategy for data analysis, I should get the same pattern of results. This is a direct replication. Okay? So I just literally rerun your experiment. I will probably not get numerically identical results because there's variability. If you're working in sort of biological sciences, there's some amount of variability. So I probably won't get numerically the same results, but I should get the same kind of result. And that's what the reproducibility project was doing. They, at least with my study, they tried to replicate it as closely as possible, but they were testing different people in different days and so on, so they didn't get numerically identical results. Another kind of replication or reproducibility is for the inference, right? So I don't necessarily use identical methods or analysis, but I test the same hypothesis using the same general approach. Okay? This is called the conceptual replication, where I start with the same concept, the same hypothesis, but I run a different study. If I get this conceptual replication, that's like replicating your inference, right? And this is related to the issue of robustness or generalization, right? So if direct replication should happen for any kind of robust effect. But whenever we run a study, right, we have a particular sample, and then we generalize to some population. That effect may or may not generalize, or how broadly it generalizes is an open question. So part of what this conceptual replication step or extension step is assessing that generalization, finding what are the boundary conditions, right? Does this this treatment work for one kind of cancer but not another? Does it work for men but not women? Whatever. Okay. And understanding boundary conditions is also part of science, right? It doesn't necessarily undermine the original effect. It's part of understanding what the boundaries are for that effect. Okay, so this is the terminology, just kind of general outline. Questions about these terms? Okay. All right. So I'm very influenced and inspired by Buddhist teachings, so I'm going to give you the eightfold path to achieving rigor, reproducibility, and transparency. Okay. The first part is insight, having the right view and the right resolve. And what that means in terms of science is transparency, or what's sometimes called open science. So the two big pieces here. First is to view yourself not as the owner of your methods and data, but as the curator. Okay? So we sometimes think about this as being my method, right? Like I ran a study, it's my method that I developed for this study. These are my data that I collected. Okay? Another way of thinking about this is that I'm a discoverer, right? These methods, these data are part of the world, and I have discovered them, but I don't own them. What I can do as a scientist is curate them for the benefit of other scientists, for the benefit of the scientific community, and for the public at large. Right? If you take that view, that you don't own these data, right? Stuff that I own, I keep in my house, and I only share it with people that I want to share it with. If I'm a curator, like a museum curator, then I create a way for everyone to take part in this, right? Which means to resolve to share all of these materials, data, analysis code, all of that stuff publicly, or at least as publicly as relevant for my work. There are now, thanks to the internet, maybe you've heard of it, a lot of easy ways to do this, so I'll tell you about a couple of them. The Open Science Framework is a really good one. So it's osf.io. It's very easy to use. You can post any kind of files there. So you can post, any digital files, of course, right? So if you have study materials or manuals or protocols, if you're running an experiment on a computer or some kind of machine, you can post that code, your actual data, your analysis code, your actual manuscripts or publications that come out of it. All of that can be posted on OSF. It's very flexible in that way. It's very easy to use. You just upload your files. It also has different privacy settings, which means that you can start using OSF as a repository for your project at the very beginning of the project. You can put your protocol on there before you collect any data, and you can just keep it private so no one can see it. Or you can share it with your study team, but not anybody else. When you finish the project and submit it for publication, you can include a link in your paper so that reviewers can see these materials, but no one else can. So it's still private, but accessible through a link. And then after your paper is published, you can make it fully public so that anyone can see it, whether or not they have the link. Right? So it has these flexible privacy settings. It also has a bunch of other features like a wiki page and registrations and analytics. You can see how many people are using your stuff, downloading your stuff, whatever. We have started using OSF in my lab recently. This is the OSF page for one of our studies that is currently under review. So we did this kind of thing. All of our materials and data and code are on this page, and the reviewers can have access to it, and they can see it. So that's nice about OSF. If anybody here does serious software development, does anyone do a lot of code writing as part of their research? Maybe you've heard of GitHub or GitLab. So these are other ways of sharing materials that are really great for code, for programming materials. It does source or version control. It's great for development, especially collaborative development. People can share it. GitHub is sort of the really powerhouse in this. They were recently bought by Microsoft. This is the GitHub page for one of our software projects. This is functions for reading and processing eye tracking data, one of the methods we use in my lab. This is public. GitHub in general is fully public all the time. You can make it private, but it's kind of a hassle. GitLab, which is a similar kind of thing, using a similar kind of engine, UAB has its own implementation, which means you can make it private. So if you care about privacy, I recommend GitLab. If you're okay with just your stuff being public, I recommend GitHub. It also has good integration with some software packages like R and MATLAB, where you can publish directly to GitHub. It's nice. You can also just use either field-specific archives. We do some neuroimaging work in my lab, so this is a neuroimaging repository. We also have a lab web page. We actually have 2 lab web pages, kind of a general one and a GitHub-specific one. You can post on those. And if you don't feel like dealing with web development, you can also just use ResearchGate or something like that to set up a personal page and share your stuff that way. I want to emphasize that transparency, this kind of open science, has a lot of benefits, not just to the field, but to you as a scientist. For the field, of course, reproducibility is the big advantage, right? So if you share all of your experimental materials and analysis code, other people will be able to reproduce your work directly. We all know that not every single detail ends up in the paper. You say something, but there's room for interpretation, right? If you share your actual code, then or your materials, then that's much more reproducible. For you as a scientist, this actually increases your impact, right? So whatever ambiguity is left in your published report about how the work was done, or whatever challenges are left unmet, that's a barrier to other people building on your work. If they can go to your OSF page and download your materials, then they can build on your work much more quickly. It increases your impact. And I've seen that with my own work, so I work in psychology, I study the mind and brain. Occasionally I'll get a notice that one of my studies was cited in an ecology journal or some other thing, because someone decided that something I did to analyze human behavior was useful for understanding how mold grows in ponds or whatever, and they applied it. The reason they could do that was because they could just download my code plug their data in and run it. Right? So it increased my impact well outside of my immediate field because I was sharing my materials. I mean, they were never going to read my paper about, you know, whatever stuff about psychology that they don't care about. The other benefit too is archiving, right? So especially if you start from the very beginning, that means all of your materials are organized and in a stable place, right? You don't have to worry about losing data or code. If a student from your lab graduates, you don't have to go track down their computer and look at their bizarre file structure and try to figure out where everything is and where's the new version. Is it final or is it final new? Is it final for real this time? None of that. You have to figure out a good data structure from the beginning, or good file structure, put that in a public place or semi-public place, and you have an archive of it. You don't have to worry about computer crashes or any of that kind of stuff. So these are advantages for you, the archiving and the increasing the impact, in addition to the field. There's also a push, certainly in psychology, it takes a long time to get papers published. Review cycles are very long. And so people are moving into using preprint archives. So at the time of submitting a paper or getting close to submitting a paper, people will upload their preprints. The classic one here is archive.org, which actually started out in physics, but has grown a little bit to include neighboring fields, including statistics. So we have a preprint of a stats paper from my lab on archive. There's also a bioarchive for biology and PsyArchive for psychology. So these are places where you can post your manuscripts. This is fast. It facilitates faster and broader dissemination of your work. Okay, there's no paywall here. People can just look at your work directly. And it facilitates feedback and discussion in an earlier stage. Part of my motivation in posting this is because we created a new statistical method, and I'm not really a statistician, so I wanted to talk to other people in the field about it. And so I posted it there, and then I started emailing my colleagues out in the world and saying, hey, you guys know a lot about this. Can you take a look at this and tell me if I'm crazy or if this thing's actually going to work? I wasn't crazy. So that was great, right? I got that feedback. All right, that's the transparency and open science piece. And a lot of that is about perspective and how you see your work and how you share your work. The next part is about how you talk and conduct your work. And here the key thing is registration or pre-registration. What this forces you to do is to, or encourages you to do, I guess, is to conduct and describe your study as it was planned, right? Remember that cycle we talked about at the beginning, right? You generate your hypothesis, you design your study, you collect your data, and write your report. If your report is registered, that means that all of those earlier steps are described in the registration, okay? It also allows you to be explicit about exploratory aspects, right? So this isn't about avoiding exploratory work. You can do all the exploration you want. You just have to say, here was our hypothesis, here's what we did to test that hypothesis, here's a bunch of other cool stuff we discovered later. Probably the most well-known, I'm sure well-known to most of you, is clinicaltrials.gov for registration of clinical trials. That's great for registering clinical trials. But there's other forums. OSF in particular has a registration forum. So if you're not running a clinical trial, but you want to register your study, you can do it on OSF. There's other places to do it too. One of the ways you can do this is actually through journals. Many journals are now doing registered reports as an article format. Okay? And the way this works, so according to the Center for Open Science, now there's over 100 journals, 120 journals that are doing this kind of thing. The way it works is you develop your idea, you design your study, and then you submit basically the intro and methods of your paper to the journal. It goes out for stage 1 review, you get feedback. If it's accepted, you get a provisional acceptance. Then you run your study, collect your data, analyze your data, finish the paper, submit it, And at that stage 2, really the only thing they're reviewing for is whether you did what you said you were going to do. Right? So the paper is accepted on the basis of the strength of your motivation and your methods, not on the basis of your results. And this is a way to overcome the publication bias problem, right? If you have a good idea and a good method for testing that idea, your paper is going to get published. So here's a selection of journals that are doing this kind of thing. A lot of them are in psychology or behavioral sciences, neuroscience. There's a bunch of medicine and health journals on there. Lots of them are doing it. This probably seems weird as a publication model, but it's not that weird if we think about other domains, right? So with our students, we have them come up with a thesis idea, write a proposal, committee reviews the proposal. If it's approved, they go and they run their dissertation project, and if they did what they said they were going to do, they get their degree, independent of whether the results come out as predicted or not. When you submit a grant, you have an idea, you design the study, you submit the grant, it's reviewed. If it's funded, you get the money, you get to do the project. If the project doesn't work out, if your hypothesis is not supported, it's not like NIH is going to take their money back, right? So it's applying that same idea to journals, to the publication model. Of course, the benefits here for the field are pretty obvious, right? It avoids the p-hacking and harking problem. It allows you to distinguish in a transparent way which were the planned analyses and which ones were the exploratory analyses. The registered reports have advantages. I saw some nods, so I think people are already getting this, right? So first of all, you get feedback before running your study, right? And if you've had this situation where you submit a paper and the reviewer says, well, what you should have done, you're like, oh, what am I going to do, run a new study now? Well, it would have been nice to get that feedback before you ran the study. Study is evaluated based on their methods, not on the results. And this is particularly good for early career researchers. And I'm thinking about like graduate students, postdocs. You know, I remember the feeling that so much was riding on whether this particular paper whether this particular experiment worked or not, and whether I got to publish that paper or not, right? It feels like a really big deal. If you do this registered report format and it gets accepted, now you're definitely getting that paper, whether the study works out or not. It's getting published, right? So some people really argue that this is a good thing. And for early career researcher, right? If you're writing a proposal for your thesis, if you're writing a proposal for a fellowship, right? You can submit that as a registered report. And if it gets accepted, you've got a guaranteed publication once you run that study. Okay, so that's virtue, registration. Last thing, last part is replication, okay? Effort and mindfulness and concentration on finding ways to run and publish replications and accepting variability. So not every study is going to replicate. My little paraphrase of the Buddha here. Actually, I don't actually know that the Buddha actually said anything like this. Non-replication is inevitable, but suffering is optional. We have to understand that the pattern that we observe in a particular sample may not generalize. It might have been a fluke. Sometimes you flip a coin 20 times and it comes up heads every time. And it could just be a fluke. That's part of life. So what are you going to do? Well, assume that any statistically significant effect is about half of what it's reported to be. Okay? I just sort of standardly make that assumption now. The Reproducibility project convinced me that this is a good rule of thumb. You read a paper, it says that there's a 20% reduction in whatever as a result of this. Assume it's 10%. That includes effects that you observe. I run a study, I get a 20% effect. Now I'm going to assume it's probably 10% and I just got lucky that time. And if I'm going to run a follow-up study, I'm going to be keeping that in mind. That, if I'm building on an effect that I've observed, it's probably not as strong as I initially observed it to be. Which means that your own findings might not replicate. I had a real, epiphany? When they contacted me about replicating my effect, I had to sort of struggle with the fact that It might not replicate. Like this paper that I published that I was pretty proud of might have been a fluke. And where I got to on that is, well, if it is a fluke, I want to know that, right? I don't want to go around building my career on a claim that turns out to be false. So I want to know the reality of it, and I want it to be verified by them, not by me, right? And now, anyone that, whenever it comes up, whenever I get an opportunity, I'm like, yeah, that fact was replicated by the Reproducibility project. It's very robust. The harder part is finding ways to make replication part of your research. Because replications are not super fun. They're not the thing that we're most excited about. We want to push the boundaries. We want to do new stuff. But we've got to find ways to do replication. So I have a couple of ideas. One is, if you read something interesting and you want to run a follow-up study, replicate the effect first. Make that, step 0 before you do anything else. And you can include that when you then run your follow-up study and go to write up the paper. Include it as a preliminary study, as a validation study, whatever you want to call it. Sometimes, in my work, sometimes my methods section will actually have a little mini experiment as part of it, because what we started with is replicating some other phenomenon that we were interested in building on, and we put that in the methods section. So we designed this study, and first thing we did was validate that we had the method right by replicating the foundation. Another way of thinking about this is that replications can be a good way of training new staff members. Someone comes into your lab, they want to learn a method in your lab. Have them run that method and replicate some prior study, either of your own or of somebody else's. Okay? That gives them a chance to learn the method, and you sort of know what they should observe, right? Because it's a replication. So it's make it part of training, and then you can, again, include it as in your publications. Questions about this? Mm-hmm.
2 questions. One going back to the preprints.
Yep.
How do the subscription journals feel about that?
Most subscription journals allow, right, when you submit a paper, you have to say that this has not been published elsewhere, right? This is the issue that you're raising. In my experience, I've been involved in these debates, and according to our survey of the field, posting a preprint in a field-specific repository is not considered prior publication. So if you submit something to PNAS, and if it's a biology paper and it's in bioRxiv, that is a field-specific repository, and they do not consider that prior publication. So they're fine with it. If you disseminate it through other means, if you do a TED Talk, if you publish it in another journal, then that's a problem. But field-specific repositories are considered okay.
And then on the registration,
Mm-hmm.
I've only heard that used in context of clinical trials. What about the rest?
Yeah, so you can register any kind of study. So clinicaltrials.gov is sort of the big repository. That's for clinical trials. There's some debate about, right now at NIH, about what constitutes a clinical trial, but setting that issue aside. That's for clinical trials. At OSF, you can register anything. It's totally open-ended. So any kind of study that you're running, you can go and register it. So OSF is sort of not, it's monitored to some degree, but it's not, it's pretty open-ended, right, in terms of, certainly any kind of study can be registered there. Registered reports, the usual stipulation is that you have not yet collected your data. So you could register a study where you have not collected your data. I think there's probably a little bit of flexibility around that. So for example, if you ran a pilot experiment for the purposes of power analysis, they would probably be okay with that. If you're doing secondary analysis of existing data, I think that's going to be hard to do a registered report with. But you can register, a secondary data analysis on OSF. That's fine. Other questions? All right, let me talk for a couple of minutes about the NIH policies. So you might have seen these notices that came out a couple of years ago. They're sort of paired. The research grant applications, those are like the R series grants, R1s, the P grants, and so on. The career development awards is K and F series grants. Okay? So these are notices at NIH. This is the document that we receive as reviewers on NIH study sections. I'm not going to be telling you secret stuff that NIH only tells their reviewers. This is public information. This particular document, I think, is like arranged for the benefit of reviewers, but all the information in it is public. This is all on the NIH webpage. So here's the guidance that NIH gives. There are two things that you need to address in your grant. The first is the scientific premise. This is the quality and strength of prior research that forms the basis for your proposed research project. This is not your hypothesis per se, it's what your hypothesis is based on. And what you need to do in your grant proposal is discuss the strengths and weaknesses of the prior research. So there's some foundation that you're building some premise, scientific premise, some foundation that you're building your work on, and you need to talk about here's what's really good, what we definitely know based on the prior work. And here's what we're really not sure about. Here's what the weaknesses or gaps are, and here's how my proposed project is going to address those weaknesses or gaps. Okay? So that's the first thing you need to do. The second part is scientific rigor, and this is the strict application of the scientific method. And this is more what I've been talking about today, the issues about reproducibility and transparency and so on. And what you need to do is describe, in your grant proposal, you need to describe the experimental controls, plans to reduce bias, appropriate to whatever it is that you're doing, and power analysis and statistical methods. They've become pretty keen on power analysis, NIH has. In my amateur statistician role, I have mixed feelings about it, but that's a separate talk. Insofar as it's possible, do a power analysis when you're writing your grant. If it's not possible, you better be ready to explain why it's not possible. The way it works on the review side is the scientific premise basically refers to supporting data. That's both supporting data that's part of the field and any preliminary work that you've done. That's the scientific premise. And on the reviewer side, if it's a R-type grant, it becomes part of your significance score. And if it's a K or F, it's part of the research plan score. Right? There's the scored criteria, right? So that it goes into significance for an R grant and a research plan for the K grant. Scientific rigor is about the proposed research itself. For an R series grant, that's part of the approach. And for the K or F grant, that's a part of the research plan. Questions about this? Yes?
On scientific premise, I mean, I may be just plain naive, but it's like, I don't see what's different from what we did. In our intro, we give a lit review to say where we're headed.
Yes. I've not read your grant proposals, but I've read many grant proposals, and what I will say is that proposals vary in the clarity with which they describe the strengths and the weaknesses. And so what sometimes happens, and has a tendency to sink proposals, is there's a lit review, but it's not super clear what aspects of the prior work are really strong or what's missing from it, and what this proposed project is how is this gonna move it forward? What is the problem in the field that this project is gonna fix? So that's the part, so there's two pieces to that, right? One is your project really well motivated? Is it really based on strong foundation? And is your project actually addressing a problem that needs to be addressed, right? So you need to be able to, your proposal needs to hit both the strengths and the weaknesses in a really clear way. So that the reviewers say, oh, this is definitely true, it's a strength of the prior research, and this is definitely missing, it's a weakness of the prior research, and this proposal is going to fix that problem. And that's sort of, those three pieces are often not clear. You're right, though, that you should have been doing this all along. What has changed recently is that NIH is being explicit. And so, like, as a reviewer, I'm instructed to comment on the scientific premise. And these are the things that I'm asked to comment on. And I'm asked to comment on the scientific rigor, and these are the things I'm asked to comment on. Questions? But that's actually all I have, so.
I'm thinking about really large studies. It seems like that's a particular challenge to do what you're suggesting, not in this aspect, not in the initial, but I've found the ones I've been involved in, if it's really large and really expensive, they try to collect as much as possible on every conceivable area. So I was on a prep study for HIV prevention, and so they were testing to see if it was efficacious in teenagers, and then they were testing to see if it reduced vitamin D and bone mass, and then they were testing that. So you end up with multiple hypotheses, and it seems like it's a little tricky to pull apart which ones were actually hypotheses of the original research and which were secondary aims or things that are analyzed afterwards in this enormous pool of data. So it seems really important what you're talking about. It seems like it needs to be much cleaner up front, the actual hypotheses.
Yeah, so this is an interesting problem. I think there's a couple of ways of thinking about it, I'm hesitant to be prescriptive about it. I'm comfortable being prescriptive about transparency and reproducibility, but not necessarily about how it's implemented for any given study. But let me tell you about different ways of approaching it. One is that you could register everything as a primary outcome. That's bad grants writing, so you probably wouldn't do that in the grant, but you can do that on OSF or on clinicaltrials.gov. The other thing you can do is, if the study is fundamentally about one thing, you can register that, and then you can have a separate registration for secondary questions that you have. Sort of building in that direction, those registrations could also happen later, right? So I mentioned, like, with the secondary data analysis, it might be hard to sell that as a registered report, but there's nothing wrong with doing that on OSF, right? You can go on OSF and you can say, there exists this data source, this data set. Here's a description of the data set. I'm going to use this data set to test X hypothesis. They have the variables that are relevant for testing this hypothesis. That's what I'm going to do. I don't know what the results are yet. I haven't run the analysis, but this is what I'm going to do. This is how I'm going to handle, data management. Here's what I'm going to do to, here's who the outliers are. I expect an interaction with gender, or I don't expect, whatever it is, right? You can register your analysis. It might seem a little bit weird to us as sort of biomedical. Is everybody here a biomedical researcher? Yeah? Maybe? It might seem weird to do it that way, but that's actually the norm in lots of other fields. So if you're doing climate science, or you're doing political science, economics research, oftentimes you're working with existing data, right? So if you're studying the relationship between mayonnaise consumption and unemployment, whatever, right? Those are data that exist in the world. You're not collecting unemployment data from the past 100 years. That's just public records, right? If you're doing climate research, you're based on data collected by NASA or whoever, and those are just existing data. What you're registering at that point is your analysis plan. So you can approach it. We can approach our work in biomedical sciences the same way and say, look, there's this existing data set, and I have a particular analysis that I want to try on it. I'm going to register that, pre-register that analysis.